Hello everyone, this is the second class on the mechanics of solids. In this class, we will study the cantilever. What is a cantilever? Cantilever is a thin uniform rod. Cantilever is a thin uniform rod clamped horizontally at one end and loaded at the other end. That is, a thin uniform rod clamped horizontally at one end and loaded at the other end is called a cantilever. The cantilever arrangement is shown in figure. This is the thin uniform rod or beam. This beam is clamped here horizontally. That is, one end of the rod or beam is clamped here. The other end is loaded with a weight W. Now this setup is called a cantilever. That is a thin uniform rod which is clamped horizontally at one end and loaded at the other end. And this is called a cantilever. Because it is loaded with a weight W is equal to mg, what happens to the beam? The beam undergoes bending. The beam undergoes bending. Let the length of the rod is L. That is, the length of the rod means from the fixed end, that is from the clamped end to the loaded end. The distance from the clamped end to the loaded end be L. Here the beam is fixed at one end and the loaded at other end. And because of the weight W is equal to mg, it undergoes bending. Now consider as AB, which represent the neutral axis of the beam. AB represent the neutral axis of the beam, which is fixed at one end A. AB represent the neutral axis of the beam which is fixed at A and it is loaded at B, which is loaded at B. Now because of this weight W, the end B deflect to a position B dash, and we can say that the beam undergoes bending. The beam undergoes bending. How much the end deflect due to the weight W? This is given by the depression delta at the free end of the cantilever. Depression delta at the loaded end of the cantilever. How much is the end deflecting? Now consider a point P in the beam which is at a distance x from the fixed end. Now the depression at this point is y. In the figure, the schematic diagram is shown. Here the length of the rod is L. That is, length of the rod means the length of the rod from the fixed clamped end to the loaded end. A is the fixed end and B is the loaded end, and the distance between A and B is L, and it is loaded by a weight W at the end B. Because of the weight W, the end B deflect to a position B dash so that the beam undergoes bending. Now how much the end B deflect to a position B dash? That is given by the depression at the free end of the cantilever. And in the present case, we have to find out the depression delta at the free end of the cantilever. So what is our aim here? We have to find out the expression for delta. What is delta? Delta is the depression at the free end of the cantilever. When the cantilever is loaded at the end L, that end will undergo deflection. Suppose the position is changed to B dash. Now, how much the end is deflected? That is given by the depression delta. And we have to find out the expression for this depression delta. That is our aim. So we have to find out the depression delta at the free end of the cantilever at x is equal to L. To derive the expression for this delta at the free end of the cantilever, we have to use certain relation, that is at x is equal to 0, y is equal to 0. What is y? Y is the depression at a distance x. Here, y is taken at a point P. Y is actually the depression at a distance x. Now at x is equal to 0, there is no depression, because at x is equal to 0 means it is the clamped end where the beam does not undergo any deflection. So the depression at A is equal to 0. So we can say at x is equal to 0, y is equal to 0. Since y is equal to 0, we can say that dy by dx is also equal to 0. Now at x is equal to L, x is equal to L means it is the free end of the cantilever or the loaded end of the cantilever where the depression is maximum. We have represented the depression by y. Now what is the depression at the free end? At the free end x is equal to L. Now the depression is given by delta. So we can say that the depression at the free end is y is equal to delta. Also, you have to use the relation 1 by r is equal to d square y by dx square, where r is the radius of curvature of the neutral axis. So you have to use these three relations to derive the expression for delta at the free end of the cantilever. Now how to find the expression for delta? Delta is the deflection of the end B by the application of the force or weight W. To derive the expression for delta at the free end of the cantilever, you have to use the equation. At equilibrium, the external bending moment is equal to internal bending moment. At equilibrium, the external bending moment is equal to internal bending moment. External bending moment means moment because of the external couple, and internal bending moments mean moment due to the restoring couple. In the previous class, we have seen that the internal bending moment is equal to yig by r, where y is the Young's modulus of the material of the beam, ig is the geometric moment of inertia, and r is the radius of curvature. Already we know the expression for internal bending moment. Now we have to find out what is the external bending moment. To find out the external bending moment, consider a section of the beam at P. You consider a section of the beam at P. Now P is at a distance x from the clamped end. Consider a section of the beam at P at a distance x from the end A, that is a fixed end. This is the section you have to consider. This is the section you have to consider, and P is at a distance x from the end A. We have given a weight W at the end B, and as a result, the beam undergoes bending. So there is an external couple. Why the beam bends? Because of the external couple. Now what is the value of this external bending moment? Moment means force into perpendicular distance. Here the force is W, which is equal to mg, and the perpendicular distance is the distance taken from the point P to the loaded end. The perpendicular distance is taken from the point P under consideration to the loaded end. So the external bending moment is force into perpendicular distance, that is here W into L minus x. Now what is the internal bending moment? We have already derived the expression for the internal bending moment, that is equal to yig divided by r. Yig divided by r is the internal bending moment. At equilibrium, the external bending moment that is responsible for bending balances the internal bending moment because of the restoring couple. So let us equate this external bending moment with the internal bending moment. That is, at equilibrium, you can say W into L minus x, that is equal to yig divided by r. This is our first equation. So remember our aim, we have to find out the depression delta at the free end of the cantilever. From the equation, we can have 1 by r is equal to W L minus x divided by y into ig, where r is the radius of curvature of the neutral axis when it undergoes bending. Now we use the equation 1 by r is equal to d square y by dx square. 1 by r is equal to d square y divided by dx square, that is equal to W L minus x divided by y ig. So we are getting an equation d square y by dx square equal to W L minus x by y ig, where y is the depression at a distance x and a capital Y is the Young's modulus of the material of the beam. Now let us integrate this equation. On integrating, integral of d square y by dx square is dy by dx. So LHS become dy by dx. What is RHS? W by yig, which is a constant. Now let us integrate integral L minus x dx. L is a constant. So this is equal to W by yig, then Lx minus x square by 2 plus the constant of integration C1. Now let us evaluate C1. What is the value of C1? To find that, use the boundary condition, that is at x is equal to 0, dy by dx is equal to 0. That is at the clamped end or at the fixed end, x is equal to 0 and the dy by dx is also equal to 0. At x is equal to 0, dy by dx is equal to 0. Therefore, what happens to the above equation? First, substitute dy by dx is equal to 0. That is, LHS becomes 0. LHS becomes 0. 0 is equal to W by yig into yig into, now substitute for x is equal to 0. That is L into 0. L into 0 minus 0 square by 2 plus C1. So what is our result? This implies that C1 is equal to 0. That is the constant of integration, that is equal to 0. When C1 is equal to 0, the above equation modifies to dy by dx is equal to W by yig Lx minus x square by 2, because there is no C1 because C1 is equal to 0. So dy by dx is equal to W by yig into Lx minus x square by 2. So we have the equation dy by dx is equal to W by yig Lx minus x square by 2. Now do the same procedure. Integrate this equation one more time. Now integral of dy by dx is nothing but y. So the LHS becomes y is equal to W divided by yig integral Lx minus x square by 2 dx. This is equal to W divided by yig into L. L is a constant. Then x square by 2 minus 1 by 2. 1 by 2 is a constant. 1 by 2 into x cube by 3 plus the constant of integration C2. That is the depression at x, that is y, that is equal to W divided by yig into L x square by 2 minus x cube divided by 6 plus C2. Now again we have to find out the value of C2. Now use the boundary condition at x is equal to 0, y is equal to 0. Because at the fixed end or at the clamped end there is no depression. So we can say at x is equal to 0, y is equal to 0. Hence 0 is equal to W divided by yig. Here y is the Young's modulus, W divided by yig into, now substitute for x is equal to 0. That is L into 0 square by 2. L into 0 square by 2. 0 square by 2 minus 0 cube by 6 plus C2. This implies that 0 is equal to C2 or C2 is equal to 0. Again, the constant of integration is 0. Now, when C2 is equal to 0, the above equation modifies to y is equal to W by yig, Lx square by 2 minus x cube by 6. Because there is no constant of integration because C2 is equal to 0. Therefore, y is equal to W by capital Yig, Lx square by 2 minus x cube by 6. This is the expression for the depression at a distance x from the clamped end or fixed end. What is our aim? We have to find out the depression at x is equal to L. The obtained equation is the depression at x from the fixed end. We need to find out the depression delta at the free end of the cantilever, that is at x is equal to L. That is when x become L, the depression become delta. That is when x is equal to L, the depression y is equal to delta. That is the maximum deflection possible. Now just substitute the value of y as delta and x as L in the above equation. We will get the depression delta at the free end of the cantilever. Delta is equal to W divided by yig into L into, now substitute for x as L, L into L square by 2, L into L square by 2 minus L cube divided by 6 and this is equal to W divided by, this implies the depression delta at the free end of the cantilever. Delta is equal to W divided by yig, then L cube by 2, L cube by 2 minus L cube divided by 6 and this is equal to W divided by yig two L cube divided by 6 or delta, the depression at the free end of the cantilever is WL cube divided by 3YIG, where Y is the Young's modulus, IG is the geometric moment of inertia, W is the weight, L is the length of the rod, and delta is the depression at the free end of the cantilever. The expression is WL cube divided by 3YIG. The depression delta at the free end of the cantilever is WL cube divided by 3YIG. Now let us consider two cases. Case 1 for rectangular bar and case 2 for circular rod. What is the expression for delta for a rectangular bar? Consider a rectangular bar of breadth b and depth d. Now the geometric moment of inertia is bd cube divided by 12 that we have already discussed in the last class. Therefore, the depression delta is WL cube by 3y Ig. Now Ig is BD cube by 12. Therefore, delta is WL cube divided by 3y. What is Ig? Ig is BD cube divided by 12. Therefore, the depression delta at the free end of the cantilever delta is given by WL cube divided by 4WL cube divided by y BD cube. This is the depression delta at the free end of the cantilever for a rectangular bar of breadth b and depth d. Delta is equal to 4WL cube by y BD cube. Now for a circular rod, the geometric moment of inertia Ig is pi r raised to 4 divided by 4. Here the r is the radius of the circular rod and L is the length of the rod. Now the depression delta at the free end of the cantilever is WL cube divided by 3y Ig, and that is equal to WL cube divided by 3y. Now pi r raised to 4 by 4, and this is equal to, that is delta is equal to 4, delta is equal to 4W L cube divided by 3y pi r raised to 4. This is the depression delta at the free end of the cantilever for a circular rod of radius r.